Well, welcome to the 5.5 notes. We're going to be looking at different theorems with integrals. So just like there were theorems with derivatives we had IVT, EVT, MVT, and roles as our theorems from semester 1. There are a couple theorems we want to look at today that have to do with integrals. The first one is called the mean value theorem for integrals. So yeah, this is another MVT, but this MVT is with integrals. So we actually have a little bit different meaning, but it's still centered around that idea of average. Here's what it says. We need to be dealing with a continuous function, at least on a closed interval. This is saying that there's some number c in the interval, so c would have to be an input value in between a and c, a and b, somewhere in between, such that when we take the integral of f of x, the definite integral from a to b, which we know is representing this area underneath the curve, like this. Well, this is saying that we also get this very kind of unique answer like this. So we're going to break down what this means graphically so that we can get a little bit of understanding of what the mean value theorem is saying. Well, f of c is some height of the function f, wherever c is. So let's say c is right here, the height right there, this height is f of c. b minus a is the width of my interval. So think back to middle school. In high school, we usually call this base times height, but maybe middle school, you call it length times width. This is kind of a weird combination of height times width, but this right here is the area of a rectangle. The area of a rectangle. What this is saying is that the area under the curve will equal the area of some rectangle where the rectangle is drawn at the same interval for the width and then at some height of the function. So there is some spot on this function where the height of the function, like they drew it out here, but it's the height's determined by whatever the height of the function is at some value c. If you then take the area of this rectangle, this green area has the same area as the area under my curve. There's at least one spot where that happens. Could be even more than one, but there's always at least one as long as f is continuous on a closed interval, which is crazy. So again, what this means is that the area under the curve, or I'm going to say the area between f and the x-axis, is going to be the same as the area of some rectangle that has the same width as the interval, and then it has one height of the function, one output, which is kind of crazy to think that that's actually true, but it is. And so that's a very interesting and useful piece of information, mostly because of this next application. And again, this must be a continuous function. This must be a continuous function. Again, the area would be modeled by the definite integral, and it would equal the width times the height of the function at some number c inside that interval. Well, this leads us to something called the average value of a function. The average value of a function is basically based on this MVT for integrals. Remember, this was the MVT for integrals right here, written out symbolically. And then we can use that MVT for integrals to find what we would call the average value of a function. And just imagine that temperatures are taken continuously and they're recorded at different times. Okay, we have no unit of measurement for time here, so maybe the time is, in milliseconds or something. I have no idea. Well, that would be really drastic changes in temperature. Maybe it's hours. And maybe this is I don't know, degrees Celsius or something for the units for the temperature. But let's say we have maybe a computer system that is continuously measuring the temperature and recording the temperature as we go. Well, if we know by using the MVT that since this is a continuous function, the area underneath this temperature curve could be found by also finding the area of a rectangle that has the same width and some height of C that's somewhere inside. In fact, it might be more than one time. Like here, C could be here. C could also be here. Those are both places that have the correct height. And in this particular situation, that green rectangle will have the exact same area as the area underneath this curve. And if we find the actual height right here of f of c, this height is the average height, or in this case, the average temperature. In a really generic sense, we can call it the average value of whatever function we're measuring. This one was measuring a temperature function, so this is going to give you the average temperature. And so, I'm almost done here, Scott. I'm going to go back to that MVT for integrals really quickly and prove what we just talked about. So really, this average temperature would be the height of this rectangle, which is equal to f of c. So if I isolate f of c in my mean value for integration here, if I just go ahead and divide both sides by a minus b, I'm going to write it in kind of an interesting way like this. This is equal to f of c. This is equal to the average value. Instead of f of c, we'll call it the average value of a function. And the reason why this is an average, think about what an average means. When you're trying to find the average of something, you add it up and then you divide by the number of items in a very general sense. Well, adding it up would be our accumulation from our integral. This is adding up, combining, accumulating all of our information right here. And then we would divide by the number of items. Well, by dividing by the width, that's basically what we're doing. We're dividing by the number of items. And so that is the average value of a function. We're going to practice using that on the next video.